Section 3.4 is the derivative of the power function and another definition of the derivative. So this is the other definition of the derivative, and I had talked about part of this in class, showing that this is the same as the limit as x approaches c of f of x minus f of c over x minus c. We can do the same thing here where we're talking about x and the change of x. The change of x being the same as your h value. When we go to x and then we have another value over here, from here to here is the change of x, or delta x. So that acts the same as your h value does here. So all three of these notations, the limit as the change of x approaches 0 of f of x plus the change of x minus f of x over the change of x, same as the limit as h approaches 0 of f of x plus h minus f of x over h, which is the same as the limit as x approaches c. So all three of these definitions can be used and can be used interchangeably. So let's look at a derivative, and we want to look at f of x is equal to x to the fifth. So to find the derivative, f prime of x, I'm going to use the definition where we're looking at the limit as h approaches 0 of f of x plus h minus f of x over h. So for the function that we're using here, we need to find f of x plus h, which would be x plus h to the fifth. Now this is going to be quite a big expansion. We've got to actually FOIL out this 5 times, etc., etc. So I will go ahead and do that for you, and we find that we are going to take the limit as h approaches 0, f of x plus h, if we take all of this and FOIL it out, will be x to the fifth plus 5x to the fourth h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the fourth plus h to the fifth minus our f of x, which is x to the fifth, all divided by h. Doing our cancellation, x to the fifth minus x to the fifth leaves us with all of this, and if I divide all of my numerators by h, I am left with 5x to the fourth plus 10x cubed h plus 10x squared h squared plus 5x h cubed plus h to the fourth. And if I'm looking now for the limit as h approaches 0, if I substitute 0 for all of my h values, I am simply left with 5x to the fourth. This is the equation for the derivative of f of x equals x to the fifth. Now if I want to find the derivative at a particular place, I could now plug in, for example, f prime of 2, which would be 5 times 2 to the fourth, which is 5 times 16, or 80. What we've done in this case is we have first found an equation in terms of x. In the previous section we were plugging in our number right away, and then using that equation to find f prime at any value. I could find f prime of 1, which would be 5 times 1 to the fourth, or 5. So this is a way to find an equation for the derivative and then be able to use that in any function or for any value that we choose. Let's try another one. F of x equals x squared plus 5x plus 6. If I want to find the derivative equation for this, I need to find f of x plus h, which is x plus h squared plus 5 times x plus h plus 6 at That's x squared plus 2xh plus h squared plus 5x plus 5h plus 6. And then we're going to put it into our function for a derivative. The limit as h approaches 0 of f of x plus h minus f of x over h, substituting in the two values up top. The limit as h approaches 0 of x squared plus 2xh plus h squared plus 5x plus 5h plus 6 minus, don't forget that we have to subtract the entire f of x, so it's going to change all of the signs in that second polynomial. So now we have the limit as h approaches 0. The x squareds cancel, the 5x cancels, and the 6 cancels. Everything in that second f of x should cancel, and we should be left with just terms that have an h component. So now when I divide by h, I get 2x plus h plus 5. The limit of this expression as h approaches 0, I can now plug in 0 for h, and I get that, I'm going to work up here, I get that f prime of x equals 2x plus 5. Now, I want to take a look at both of these. So I'm going to erase. So we started with f of x equals x to the 5th, and we found that f prime of x, or the derivative, was 5x to the 4th. And then we looked at f of x equals x squared plus 5x plus 6, and we found that f prime of x equals 2x plus 5. There is a pattern here. For a power function, if we take the power and put it in front and then reduce the power by 1, we get the derivative. So if I take the power, which is 2, put it in front and reduce the power by 1, take the power, which is 1, multiply or put it in front and raise this to the lesser power, and then we can see that a constant, which is to the 0 power, if I multiply 6 times 0, I will get 0. So my final derivative is 2x plus 5. So this is a huge shortcut. Let's look at this rule. The derivative of a power function says if f of x equals x to the n, then f prime of x equals n times x to the n minus 1. So this is going to be a huge, huge savings on time. The downside of this is that it only works for power functions. We still need to be able to use our definition that we've been using for any other function than a power function. Now we will learn some other rules as we go along, but for now, this is our definition. This is a rule just for power functions. So let's try a couple using this power rule. So if f of x equals 5x to the 7th minus 11x cubed plus 12x minus 47, f prime of x, 7 times 5 is 35, drop the power by 1. 3 times 11 is negative 33, drop the power by 1. 1 times 12 is 12, and then the constant disappears. Much quicker than finding our f of x plus h and using our rule. Try this one on your own. F of x equals 35x to the 6th minus 33x squared plus 12. Turn the video back on when you've completed it. So f prime of x is 6 times 35. So we'll do that over here. 18, so that's 210x to the 5th, drop the power. 2 times 33, drop the power. The constant goes away. So that's a pretty easy rule to use. It's used for power functions, as I said. Let's look at a little more terminology. So far we've been talking about f prime of x, which is the derivative. We can also call this y prime. So instead of f prime of x, we can say y prime. So if y equals 3x squared, y prime would be 6x, using our rule. We can also use this. It is read dy dx. This is a symbol for the change of y with respect to the change of x. You can see how this comes out of the fact that a derivative is a slope at a point. So dy dx is another way of saying the derivative. We can also say d dx of y. This is read dy dx, just the way it sounds and looks. This is read d dx of y. In other words, the derivative with respect to x of our function y. And this is the derivative of y with the derivative of x. So, for example, and you need to know all four of these terms, you will see them used interchangeably. Oops, sorry. Oh yeah, that was just the last one. I'm sorry, I forgot I had it on the screen. Okay. So let's say I wanted you to find d dx of x to the 5th. You would simply tell me that's 5x to the 4th. Or if I say y equals 3x cubed minus 2x squared plus 4x plus 7, then you could say y prime equals 9x squared minus 4x plus 4. And that's it. It's a very simple section, and that's all we have to do for tonight.